we are going to start talking about MOSFETs, which I actually put all the words in the title now and didn't leave out semiconductor because that would be an important part. And today is just about kind of how they're made. So there's not a whole lot of, there is practical application, of course, but we have to start with how they're made first so that you understand how they work, so that when we actually use them, you can understand like what's going on. MOSFETs are actually kind of the transistor of choice now, especially in digital applications, and they can be smaller than other types of transistors, especially bipolar junction transistors, which is the other kind we cover in here that used to be the most popular one, but MOSFETs have kind of taken over. So if you take semiconductor devices, we spend a long time on MOSFETs and then just kind of breeze right through bipolar junction transistors, sort of, depending on who you have. I know Dr. Doss really likes MOSFETs too. So, and I do kind of. They're okay. Also, your tests are graded, so I'll give them back at the end of class. And if you are trying to run the curve fit thing in MATLAB, you have to have the curve fit toolbox downloaded. All the computers on campus here have that, but if you downloaded it and you're using it on your own computer, you may not have that, so you may need to go look for that. That's all I know about that. I did answer that one question that I had over the weekend. So let's start talking about MOSFETs. We'll get done with that, and then we'll give tests back, and then, also about lab. We have lab this week. We do not have lab next week. The week after is an individual LT-SPICE simulation lab. So, no, it's not. No, it's the MOSFET lab. Then the week after is a simulation lab. So there's like
3 weeks from that?
Yeah, so there's like no lab next week, then there is lab, then there's a lab on your own, and then we go back to I think there's 2 labs after that. And I'm sure I'll remind you of that, but I just wanted to mostly make sure you knew there was no lab next week. So now we're all good, no one will show up. So, this is the beginning of a MOSFET. It's just a big, and do bear in mind that these are actually manufactured all in one piece. So it's not like they make this and then they add stuff to it. Well, they kind of add stuff to it, but the semiconductor material is all made together. But it's easier for me to illustrate it if I kind of take it apart and start with the substrate. So we're going to start with a substrate. This one is P-type material. It can just as easily be N-type material. P-type material is actually a little more common. So we're starting with just P-type material. And then there are 2 areas of heavily doped opposite type material. So in this case, it's what we call N+, so that means it's really heavily doped. And there are 2 channels, they're not really channels. I don't want to call them channels because they're not channels, but often they are called channels, but they're really not. They're areas. I like using areas. That makes more sense. So the width of the device, you'll notice, because this is actually important when we start talking about how we characterize the device. The width is the distance from kind of the front to the back, and eventually when you look at it, the width will disappear because we'll look at a cross-section. When you look at a cross-section, you don't see the width, but the width kind of goes from the front to the back. The length is actually the distance between the 2 N areas. So it's not the entire length of the device, it's just the length between the 2 areas that are more heavily doped. So we got width and length and 2 heavily doped areas that are opposite from the P-type material. Then what gets added is a layer of silicon dioxide, and that kind of goes on top of it. I had a lot of fun with this, as you can tell. And thank you. I was quite proud because, what else is there to do in life but to make 3-dimensional moving things in PowerPoint? So after the oxide layer is added, it overlaps the N+ area a little bit, but I really didn't, put that in. Then there's metal, and metal is added in actually 4 places. There's 1 layer on top of the oxide, then there's one on top of each of the N areas, and then there's one on the bottom, kind of underneath where you see the length. Then, once that's done, we just add terminals, and those connect the metal parts to the outside of the device. Most of the time, there will be 3 terminals that you deal with, and the body terminal on the bottom is oftentimes connected to the source inside the device, so you don't actually ever access it. And there's a reason for that, but I'm not going to talk about the reason for that today. But most of the time, like the MOSFET that you have in your lab kit, you will have the source, the drain, and the gate, which are the 3 on the top. But you will not see the body connection at all. That's like connected inside the device, so you won't worry about it. So the terminals are the drain, the gate, and the source. All the current actually flows between the drain and the source. It's controlled by the gate to source voltage. So there's going to be a voltage at the gate, and then there's going to be some voltage at the source, and they're going to be different voltages, so there will be a voltage difference between the two. But there's no actual current that flows into the gate. So it's similar to the op-amp situation where you had terminals to connect to, but there was no current actually flowing into it, and the gate is also like that. There are 2 types of MOSFET. There is the P-channel or PMOS device, and that's when you have heavily doped P areas on an N-type substrate. And then there's the N-channel, which is an NMOS, which is what we looked at in the graphic before, where there's heavily doped N areas in a P-type substrate. And they do work the same way, but they have opposite voltage and current characteristics. So basically, the current just flows one way in one device and the other way in the other device. There are also differences in how they actually respond because of the charge carriers are different. In an NMOS device, electrons are primary charge carriers. In P-channel devices, the holes are, and they have different mobilities, so they will actually have different characteristics. We're going to look at a cross-sectional view. So it's been flipped to the front, so now the width has disappeared, but it's going into the screen. So just remember that. I know when I learned about MOSFETs, nobody ever mentioned that thing about the width going away, and I never saw anything other than a cross-section. It made it quite confusing. So anyway, we've got 2 areas that are heavily doped with N material. We have the gate, which is physically isolated from the rest of the structure because it's got silicon dioxide between the metal and the semiconductor. And then we have the drain and the source that are connected to those N channels. So what happens? All right, you'll notice first of all that the source and the drain actually look exactly the same. They're really constructed the same way. You can't, well, I've had this question before. Can you turn it around and use it the other way? Technically, you should be able to. However, the body is connected to the source, not the drain, so you can't. If you had a body connection outside, you might be able to, but you actually have to use it the right way because of the internal connection. So we've got this length between the 2 N areas, and the gate is isolated by this oxide layer, and this oxide layer actually has a thickness, and the thickness actually does come up later as part of the characteristic of the device. There is no current flowing into the gate, but we can apply a voltage. So the first thing we're going to do, because we need to figure out how the current gets from the drain to the source, because right now it can't. There's just this big area of P-type substrate with nothing going on. So we are going to apply a voltage at the gate and ground the other 2 terminals. So we put a positive voltage on the gate, the source is grounded, and the drain is grounded. So that's where we're starting today, and then next time we'll actually apply voltage in other places. When this happens, the positive gate voltage actually pushes holes in the P-type substrate away, and it creates this depletion region. And the depletion region is pretty much what do you call it when it's symmetrical? There we go. And you notice that because there's a depletion region, the electrons get attracted towards the positive gate voltage, and you actually get a channel between the two N areas. There's nothing flowing through there. The arrow is just showing you that it's there. Yes?
Why is the channel only that size and not the size of the entire depletion region?
Oh, because if it was the size of the depletion region, then it wouldn't work. It's actually just this little area between that positive gate voltage and the depletion region. It's just an area where the charges have collected, and it just creates that small area, but not the whole depletion region. That's different. So once you get that going on and you get that kind of channel, you can eventually have current flowing through there. Not today, but eventually you can. So you can see how if you do something, you could get stuff flowing from one N area to the other N area, and that's what we did. Also, bear in mind that the N channel actually occupies that entire area under the oxide layer. So it's not just a little thin, narrow area. It's a big, huge area that occupies all that area under the oxide layer and kind of allows for a large area for current to move. So it's not just like it's a little creek. It's more like a river. So how we characterize these, how we figure out kind of how the current's going to move, one of the things that we look at is the ratio of the width to the length, because that tells you how big that channel is to allow current to flow when it flows. So for the most part, the lengths are between 0.03 micrometers and about 1 micrometer, so not very big. And we have about 0.05 micrometers to 100 micrometers for the width. So interestingly also, the width is generally bigger than the length, because the length is not the length of the old device, it's just between those two N areas. So what ends up happening is we need a minimum value of gate to source voltage to create this channel. If you just have a little bit of voltage, it's not quite enough. You need to get to a certain voltage. It's called the threshold voltage. Don't confuse. Don't confuse the threshold voltage VT with the thermal voltage VT. They're two different things. What I try to do is put a little t for threshold and a big T for thermal, but I don't always remember. But context is everything. So we had, when we were dealing with diodes, we dealt with the thermal voltage. When we deal with BJTs, we will deal with the thermal voltage. With MOSFETs, we will deal with the threshold voltage. So they just bear that, and I'll try to make it as clear as I can. Threshold values, 0.3 volts to 1 volt. However, if you are doing an academic exercise, you can create any value you want. So don't expect it always to be between 0.3 volts and 1 volt. That limits instructors to too narrow a range. And when we get the gate to source voltage above the threshold voltage, we have something known as the overdrive voltage. And that's only just the difference between those two values. We use that more for ease of writing out equations than we do to actually conceptually do anything. So there's a lot of equations that take the difference between the gate to source voltage and the threshold voltage, so we just give that a name to make it easier to calculate different values. You might imagine that if you have a metal and an oxide and a channel, that you might be able to form some kind of capacitance between those two areas. If you think about it, if you have the metal or the gate, that's going to be positive. If you have the oxide, that's like a dielectric, and the channel has negative charges in it, and you can actually create a capacitance in that region. And that capacitance is always going to be there, and it's based on the thickness of the oxide layer, which is why that was denoted earlier, because that does determine what the capacitance is. And it's also based on the permittivity of the oxide. So we can calculate The capacitance, however, when we talk about capacitance, we're not really finding capacitance, we're finding capacitance per unit area. So don't make the mistake of thinking that sometimes there's a C prime that sometimes is used, but oftentimes it's just called capacitance, but it's really not in farads. It's really in farads per square meter. Unless you know what the width and the length is, then you can say what the capacitance is. But and we know what the permittivity of the oxide is, so that's not too difficult. So just as an example, and this is my only example for the day, and it's the last thing I'm going to say, because next time I'm going to talk about what happens when we actually apply a voltage, and I want time to give back tests and that kind of thing. So let's say we have a thickness of 4 nanometers. We can easily calculate the oxide capacitance per square meter by just taking the permittivity of 3.45 times 10 to the minus 11 and divide by the thickness, which is 4 times 10 to the minus 9, and we get 8.6 times 10 to the minus 3 farads per meter squared. Meter squared really doesn't make a lot of sense when you're dealing with small devices. We don't have square meter MOSFETs. We have teeny weeny little MOSFETs. So we change it a little bit and generally reference it per square micrometer. So when we do that, we have 10 to the minus 6 on the bottom squared, so we have to put 10 to the minus 12 on the top to make it come out right. So then we have 0.0086 picofarads, which is actually 8.6 femtofarads, but I didn't put that in as yet, but that is what it actually is. So if you had a gate that you actually knew the length and width of, you could find the actual capacitance by just multiplying by the width and the length, and that would give you the actual capacitance in femtofarads, actually. So it's very small.